So thank you for the presentation. Good morning, everyone. I'm going to show the work about the role of dynamical noise power in complex neurophysiological systems. This research being developed with the help of engineer Vincenzo Catrambone, Professor Claudio Bonanno, and Professor Gaetano Valenti. So traditionally, noise has been always regarded as a negative feature since it has been I was saying noise has been always regarded as a negative part of a signal, since it has been regarded as random disturbances that affect a signal. But in recent years, noise has been positively reevaluated. In the sense, it carries information about the stochastic part of the system we are observing. This stochastic part is not predicted or cannot be predicted by its deterministic part or from its past history. From a physiological viewpoint, this noise seems to be involved into signal transmission or detection performance, and in sensory, nervous, and cardiovascular systems. Despite this noise importance, we don't have in the literature a clear definition and quantification of physiological noise. So we require, first of all, that our physiological systems to be studied through time series, which are substantially measurements of the phenomenon of interest with samples ordered in time. And the main assumption here is that we suppose our time series to be an output of an unknown metrical and deterministic dynamical system described by a map. In this case, we can formalize physiological noise as the dynamical noise, namely a sequence of independent and identically distributed random variables that given probability, which these random variables modify the dynamics at each iteration according to the following equation. For what concern the state of art, in the literature we find lots of works about the output measurement noise, which deals with the negative conception of noise, and which is substantially a noise, which is substantially disturbances added to an exact signal. And noise estimation identification is almost straightforward in some cases. We are actually interested into dynamical noise, which I recall may be considered as an intrinsic component of the system we are studying, and it is involved into the signal series dynamics. It carries information about the stochastic process that cannot be predicted by its deterministic part. And in this case, in order to estimate this kind of dynamical noise, we should require information about its deterministic part. So we should have information about the map T. So we asked ourselves, okay, so we asked ourselves, is it possible in physiological systems where generally the deterministic part is not available, is it possible to perform a physiological noise estimation or dynamical noise estimation when the map is unknown, when we don't have any a priori knowledge about the map T? Sorry, the answer, some latency. Sorry, the answer is is positive if we use some information theoretic and nonlinear tools. So we started our investigation by seeing the effect of noise disturbances according to some complexity quantifier. In this case, we used the well-known approximate entropy quantifier, which is related to the well-known Kolmogorov-Sinai entropy. And we did the following. We injected Gaussian dynamical noise into logistic maps with parameters 3.5 and 4, which correspond to the periodic and chaotic regimes. And then we depict the approximate entropy profiles, which is nothing but the curve of the function approximate entropy as function of one of its parameters, namely the radius or the tolerance. And we noticed better that when noise injected, the approximate entropy profiles generate peaks, and the higher is the levels of the higher are the levels of noise, the higher are these peaks. And if we compare the in panels C and D, in this case we depict the approximate entropy profiles for two physiological signals, one gathered from cardiac dynamics and the other one from brain dynamics. And by depicting these approximate entropy profiles, we saw that these peaks are generated as in the case of synthetic data perturbed by the dynamical noise. We actually believe that these physiological signals are actually corrupted by dynamical noise. So we stated the proven theorem, which briefly says that it is possible to relate the dynamical noise level inside a time series, inside a noisy time series, with the shape of the approximate entropy profiles. To be more precise, the approximate entropy profiles scales like the curve minus logarithm of the tolerance when this tolerance or radius starts to see the noise effects. And this theorem holds for any distribution, for any probability density function for the dynamical noise. And in the particular case, or better, if we assume that our dynamical noise follows a Gaussian distribution with zero mean and a fixed standard deviation, it is possible to estimate this standard deviation in an enclosed form. So starting from these theoretical results, we developed a simple algorithm in order to perform noise estimation, which works as it follows. Firstly, the algorithm takes as input a noisy time series. Then we depict the approximate entropy profile as function of one of its parameters, namely the radius. Then we search for the tolerance point where the approximate entropy profile scales like the curve minus log R, minus log the tolerance. Then, if we have if we make assumptions about the noise distribution into the time series, we can improve our previous estimation by curve fitting methods. Okay, so we validated our results on series gathered from synthetic data, from analytic equations, sorry, where we have injected different levels of dynamical noise. And also this has been validated on logistic maps in chaotic regime, so with parameter lambda equals to 4, and also on Popomanville maps perturbed by dynamical noise, and also on autoregressive models. And we see from these box plots that the method actually recognizes and distinguishes the levels of superimposed noise with a minimal dispersion across its median value. So then we we applied the method in cardiovascular dynamics, in particular on heart rate variability series, which briefly are series gathered from ECG and this series represent the interbeats time interval from the interbeats time interval, or better, the distance between, the distance in time between two R peaks of the ECG. And these series are known to represent the nonlinear cardiovascular dynamics. We found that median noise levels in heart rate variability series increase along with pathology. If we compare the median noise levels encountered in subjects with congestive heart failure and atrial fibrillation subjects with respect to the healthy cohort. Then we have also applied this method in brain dynamics, and we saw that in this case median noise levels are actually higher in mental arithmetic tasks with respect to the resting state, almost on all the scalp. And to conclude, I want to stress the fact that noise drastically changes, noise, whether physiological or dynamical, drastically changes, modifies the series dynamics and the complexity. And for this reason, noise should be regarded as a potential complexity quantifier, which is independent on the series deterministic dynamics. To illustrate this fact, if I inject the same dynamical noise on logistic maps with parameters 3.5 and 4, which are known to be, as I recall, in periodic and chaotic regimes, then I find the same levels of noise, but if I analyze this series through complexity quantifier, in this case I used the approximated quantifier, I see that I have an inversion of the expected behavior, since periodic dynamics, even perturbed by dynamical noise, should be in some sense more regular than chaotic ones. With this, I'm done. I hope you enjoyed my presentation, and I'm here for some questions.
Thanks. There are questions?
Hi, thank you for your talk. I'm not sure I fully understood the whole approach, but what strikes me is how can you define noise in these physiological signals, in the sense that what do you know about the deterministic part? How can you, because also in different situations, the deterministic part can be made of many components. I'm just asking what is the what is the approach there?
Okay, so I'm going back to slide. Okay, thank you for. Surely I will give you some details later. But the main advantage of this method is to compute noise when we don't have access to the. So if we look at this approximated profile, if I don't have any level of noise, I see that for logistic map I have a plateau. But in this case I don't know what is the dynamics, and I expect this for almost any system. When I add some dynamical noise, this plateau is broken, and these peaks are due to noise. So we, in a certain sense, we do not consider the deterministic part, and we also see these effects, the effects of noise. So we want to quantify the slope of this curve, which are due to the presence of noise. Maybe I will give you some details later, but this method has been this is a model-free method in order to estimate the noise presence in dynamical systems when these time series are supposed to have a deterministic part and a stochastic part, which acts in a dynamical way.
Okay. There are other questions? Okay.
A quick question. Did you try other values for the parameter, the logistic map, by any chance? Because you tried the lambda 3.5 responds linearly, the map, and in the chaotic it responds linearly, but there are in the middle, the response to the map is not linear.
Okay, I just took here two examples. I just took two extrema.
Sorry?
I considered the two. Oh, sorry. I considered only the two extrema. So when I have a regular dynamics and a chaotic one, but I can extend.
Yeah, because it is known that for lambda equals 4, it responds linearly, which is the same. No, from a dynamical point of view, is the same regime.
Okay, but
you should try in the middle.
Yes.
To validate the method.
Yes, but with lambda equals to 4, I have chaotic behavior of the
It responds linearly because so you, if you apply a small perturbation, the map will respond linearly to the perturbation. It does the same thing for 3.5. In the middle, it won't be like that. So in principle, from the response point of view, you have the same you are in the same regime. They are not two different regimes, although it is chaotic. But it responds linearly to an external perturbation. Okay, so they are the same regime. Try in the middle as well.
But they have two kinds of Kolmogorov-Sinai entropy. One is with entropy positive, and one with entropy 0. Okay. In order to consider other maps, I also performed these simulations for moment maps, which are intermittent maps also.
Okay. We thank again the speaker.